Hi, my name is Nadav Schneider, and today I'm going to present you our work, Explainable Deep Multiview Methodology for HEDP form quality assessment. But first, I want to thank my collaborators, Muriel Tzdaka, Galit Strum, Lazovski, Galit Gilad Oren, Gvishi, and Oren. So first, I will present the material itself, then the problem around it, and finally our suggested solution. So aerogels forms are a large family of materials, generally defined as extremely low density solids. Their name is derived from the fact that they are formed mostly from air and also from gel. So it's 95% air and 5% gel. The sponge-like structure of material has very unique sets of properties that allows advances in many applications. I will go over some of them. So in the top right of the screen, you can see an example of thermal insulator made from aerogel that blocks the heat from passing through. Aerogels can also be helpful for drug delivery, for preventing the drugs from being damaged in the package. And another interesting application is HEDP measurements. I will elaborate on it in the rest of this talk. Other than HEDP, aerogels are helpful for collecting and analyzing high-speed dust movement in space. Aerogels are useful for biomedical applications, and etc. etc. So what is HEDP? HEDP is high energy density physics. Those are experiments that deal with extreme pressure scenarios. For example, the Earth's core, the Sun's core, etc. And in this pressure, rich physics is present, which is important in understanding, for example, how stars form. So those experiments usually involve a dynamic wave propagating inside a low-density foam inside this aerogel, and therefore it is crucial to ensure that the used foam is not defective. A significant limitation of dry aerogels foams is mechanical fragility, and they tend to suffer from cracks. We say that the foam is defective if there are scratches, dirt, or dark stains on the top or the bottom of the foam, or if there are holes in one of the profiles of the foam. These properties indicate that there is deep hole in the foam, and it is crucial to look at the foam from multiple views to understand whether there is such big hole. Otherwise, this will be similar to observing only the top of the iceberg. So we have to look all around it in order to decide whether the foam is defective, normal, or even normal defective. Those are forms that are neither exactly normal nor defective and are not well defined. So now we move to describe the prepared dataset. Unfortunately, it has some significant limitations which are common to the real-world problems. It has only 123 examples. In each example, there are 5 images from different views. The data is unorganized, and there is a variance in the imaging conditions and settings, different lightings, and more. Since the amount of the data was tiny, we considered a relaxed problem in which there are only 2 classes, normal and defective. So we also converted the normal defective foams to the defective label under the assumption that if there is a doubt, there is no doubt. Here are some additional examples from the dataset. We can see here that there is a significant variance between the imaging conditions. And so, in order to classify the quality of a given foam, experts must search for these problematic properties, and they're usually required to measure the sizes of the stains or scratches on top of the images. This long and tiring task cannot be done repeatedly and infinitely by human experts. This procedure is also prone to subjective errors, especially on the normal defective forms. So here we can see 3 profiles from different forms. There are barely any differences between them. However, they are labeled with 3 different quality labels. From left to right, we can see a normal form, a profile, a normal defective, and then on the right, a defective form. So the desired goal will essentially consist of 2. The first is an automatic tool that will properly classify the quality of each form, and this will be done based on multi-view perspective and multi-view architectures. I will explain about them in the next slides. And the second is to provide an explainability for those models. Why did the model decide what it just decided? This is an interesting question that many physicists are interested in it. The overall flow will be as follows. First, images from different views are acquired using a focal microscope. Then a multi-view model gets them, and in the output we have an inference, classification, whether the given form is normal or defective, and explainability, an explanation on why the model had this specific decision. This is the classical approach of multi-view, where every single image from the sample is forwarded into a single CNN. The architecture that was chosen in our case is ResNet 34, and each forwarded view resulted as a feature map is aggregated into a max pooling layer called view pooling, and then the generated feature vector is forwarded to a classifier block. In our case, the classifier consists of 2 fully connected layers. Unfortunately, an initial attempt to run this model led to an overfit. One of the major reasons for overfit is significant irrelevant variance between examples. So we did a pre-processing. For example, we convert the images to grayscale since the color is irrelevant for classification. We quantize the intensity into 10 bins. We do this to minimize the influence of differences between similar pixel values. And we even extracted the bounded circle you can see at the bottom of the slide because the background is not relevant. Then we suggest 4 multi-view architectures. Each has its own assumptions and suited to another problems. So from left to right, the first one is a completely similar views, or CSV. We assume that each view is visually similar to the other views, and therefore a single feature extractor, a single CNN, will be trained on all of them, and will be tuned to extract the features from all of them, and this is sufficient. In our case, obviously this is not true, since we can see that the profiles and the top-bottom pictures are visually different. The second is similar subgroups, or SSG, where we assume that we can split the views into subgroups. So this is the correct architecture for our problem. Later we can see partially similar groups, which is somewhere between similar subgroups to different views. And finally, completely different views assumes that every view is visually different, and therefore a different feature extractor is needed. Before training the models, we split the dataset into a 70-30 train-to-test ratio. And as we can see, the best deep learning model is the similar subgroups, or SSG architecture. This architecture has the correct assumption for the given task. It has two CNNs. Each of them is fine-tuned to extract the relevant features for each subgroup, and therefore it converges the best and also has the best accuracy and AUC. Now, multi-view explainability is challenging since the features from the different views are mixed inside the view pooling layer. Nonetheless, we suggest an innovative methodology to explain multi-view models. So I will present this methodology. And first, we do the fine-tune of the multi-view model with the chosen architecture. In our case, similar subgroups architecture. Then, after we fine-tuned, in this case, both of the CNNs, each on different views, we freeze the weights of the CNNs in each subgroup. We duplicate the freezed CNN for each view and each subgroup and concatenate a classifier. Then we fine-tune the resulted one-view models. Each model gets its own view. So here we have 5 one-view models. 3 out of them, 3 profiles, have one CNN, with its freezing weights, and the other subsection, the other subgroup, with the other CNN, and again with freezed weights. And finally, we activate a model agnostic explanation, for example, line. So you can see the input and the output there. The explanation is resulted as a color of the contributing areas, and this is actually the explainable block, the CNN, the freezing of its weights, and the classifier. Since we do another fine-tune on one view only model, from the definition of multi-view, we cannot predict the classification correctly, as the model has to observe all the views for sufficient information to classify correctly. So there is a trade-off. We cannot use the one-view models for classification. The classification is damaged, but we can extract the relevant features from the fine-tuned CNN that was fine-tuned on all of the views to extract the areas that contributed to whether a damaged or normal, effective or normal form. So we cannot say which area contributed to which label, but we can say that the model focused on these areas through the final decision. For future work, we intend to try our multi-view architectures and explanation methodology on different scientific domains, and in addition, incorporating human-in-the-loop approaches that will help the model achieve better results. Thank you very much.